Mass and energy analysis of control volumes. This topic introduces the concept of mass and energy analysis for control volumes in thermodynamic systems. This approach is used to analyze open systems where mass and energy cross the system boundaries. The main focus is how the conservation laws of mass and energy are applied to flow systems. This concept becomes the foundation for understanding devices such as turbines, compressors, and heat exchangers. The entire discussion is based on mass and energy balance principles.
Lesson Plan Thermodynamics 1. The course structure is arranged progressively from basic concepts to more complex system analysis. The sequence starts from basic concepts, pure substance properties, and continues to the second law and entropy. The control volume chapter comes after mastering closed system analysis. This structure ensures a logical and systematic learning progression. Each chapter builds the foundation for the next analysis.
Learning outcome. The learning outcomes emphasize the ability to apply mass and energy conservation to various systems. Students are expected to distinguish between steady and unsteady flow. The concept of flow energy and enthalpy becomes an essential part of the analysis. Engineering devices such as nozzles, turbines, and heat exchangers serve as application examples. The final goal is to solve real engineering problems systematically. Mass conservation in reactions. The law of conservation of mass states that total mass before and after a reaction remains the same. This principle applies to closed systems without mass loss. The hydrogen and oxygen reaction example shows that the product mass equals the total reactant mass. This concept becomes the foundation of all mass balance analysis. In flow systems, the same principle still applies even though the system form is different. Normal velocity concept. Normal velocity is the velocity component perpendicular to the control surface. This component determines how much fluid actually crosses the surface. If the flow is not perpendicular, only part of the velocity vector contributes to mass flow. This concept is crucial in mass flow rate calculations. Misunderstanding the velocity direction can lead to significant analysis errors. Check your understanding number 1. This question reinforces the definition of normal velocity in the context of control volumes. The key idea is that only the perpendicular component contributes to flow across a surface. This concept is often a source of mistakes in early calculations. Understanding velocity vectors and their projections is essential here. Mastering this concept simplifies more advanced flow analysis. Average velocity in pipes. Average velocity is used to simplify non-uniform velocity profiles in pipes. This value represents a single velocity that produces the same flow rate. This approach is very practical in engineering analysis. Without this concept, calculations would become much more complicated. Average velocity forms the basis for mass and energy flow rate calculations. Volume flow rate. Volume flow rate represents how much fluid volume flows per unit time. This quantity is calculated as the product of cross-sectional area and average velocity. This concept is widely used in piping and pump systems. Changes in area or velocity will directly affect the flow rate. This understanding is important before moving to mass flow rate concepts. Mass conservation in a bathtub. The bathtub example shows a simple application of mass balance. If the inflow rate is greater than the outflow rate, the mass of water in the tub increases. If the outflow rate is greater, the mass decreases. The change in mass inside the system always equals the difference between inflow and outflow. This example helps visualize the control volume concept intuitively. Control volume analysis. A control volume is a selected region in space used to analyze mass and energy flow. Its boundary is called the control surface, where mass and energy can cross. For more precise analysis, small differential elements of volume and surface area are used. This approach allows the formulation of general mass balance equations. This concept becomes the foundation of all flow system analysis. Control surface orientation. The orientation of the control surface affects the simplicity of mass flow calculations. When the surface is perpendicular to the flow, the entire fluid velocity contributes directly to mass flow. When the surface is inclined, only the normal component of velocity is effective. This adds complexity because velocity vector projection is required. Therefore, choosing an appropriate control surface orientation is highly recommended. Answer B. Align control surfaces with the flow direction to avoid unnecessary complexity. Explanation. A. Use control surfaces at an angle to the flow direction for greater accuracy. This is incorrect because using control surfaces at an angle increases complexity in calculating the normal velocity component, which is unnecessary if the surface is aligned with the flow direction. B. Align control surfaces with the flow direction to avoid unnecessary complexity. This is the correct answer because aligning the control surface with the flow direction simplifies calculations by directly considering the normal velocity component. C. Always position the control surface perpendicular to the flow to reduce calculations. This is incorrect because positioning the surface perpendicular to the flow direction may complicate mass flow calculations as the normal velocity component needs to be projected. D. Position control surfaces randomly to account for all potential flow variations. This is incorrect because random positioning of control surfaces introduces unnecessary complexity and does not simplify the analysis of mass flow. Mass conservation in steady flow conditions. The mass flow rate entering must equal the mass flow rate leaving. There is no mass accumulation inside the control volume over time. The example with 2 inlets and 1 outlet shows that the total mass flow must be balanced. This principle is a direct application of the law of conservation of mass. The steady flow assumption is crucial to simplify the mass balance equation. Mass and volume flow in steady flow. Although the mass flow rate remains constant, the volume flow rate can change. This change occurs because the fluid density changes during compression or expansion. In a compressor, the outlet volume flow can be smaller even though the mass flow is the same. This shows the important difference between mass and volume concepts. This understanding is critical in gas system analysis. Flow work concept. Flow work is the work required to push fluid into or out of a control volume. An imaginary piston concept is used to visualize the force due to pressure. The magnitude of this work depends on the pressure and the fluid volume being moved. Flow work is always associated with open systems. This concept becomes the basis for introducing enthalpy. Force balance in piston system. The force acting on the piston comes from fluid pressure multiplied by the cross-sectional area. Under steady conditions, there is no acceleration, so the piston force and fluid force are balanced. This balance ensures that there is no change in piston velocity. This analysis neglects friction and inertia effects. This approach simplifies the understanding of the relationship between pressure and force. Flow work in control volume. Flow work represents the energy carried by fluid as it crosses the system boundary. Before entering the control volume, energy is required to push the fluid against pressure. After entering, fluid pressure helps maintain the flow. This energy becomes part of the total fluid energy. This concept explains why flow energy cannot be neglected. Check your understanding number 3. This question reinforces the physical meaning of flow work. The key idea is that energy is required to push fluid into or out of the system. Pressure acts as the main mechanism that maintains the flow. This concept is often not intuitive for beginners. Therefore, conceptual understanding is essential before moving to the energy equations. Energy components of fluids. A non-flowing fluid only has internal, kinetic, and potential energy. A flowing fluid has an additional energy term called flow energy. This flow energy is directly related to pressure and specific volume. This difference is very important in open system analysis. Without including flow energy, the energy balance would be incomplete. Energy transport by mass. Energy can be carried into or out of a control volume by mass flow. The amount of energy transferred is proportional to the mass flow rate and the specific energy of the fluid. This concept is very important in the analysis of turbines, compressors, and heat exchangers. With this approach, energy flow can be calculated systematically. This becomes a central part of the open system energy balance equation. Steady-state operation. Steady-state operation means the system conditions do not change with time during operation. Power plants are designed to operate in this condition to ensure stable power output. In this condition, mass and energy flow rates remain constant. This simplifies the analysis because there is no accumulation term in the balance equations. This concept is very important for large-scale energy systems. Steady flow control volume. In steady flow conditions, the mass inside the control volume remains constant. The energy stored in the system also does not change with time. All mass and energy entering are balanced by those leaving. There is no net accumulation inside the system. This assumption makes the mass and energy equations much simpler. Fluid properties in steady flow. Under steady flow conditions, fluid properties at the inlet do not change with time. The same also applies to the properties at the outlet. This means temperature, pressure, and velocity remain constant at each boundary point. This condition greatly simplifies engineering calculations. Without this assumption, the analysis would become much more complicated. Answer: B. Fluid properties at both the inlet and exit remain constant over time in steady flow. Explanation: A. Fluid properties at the inlet vary over time, but remain constant at the exit. This is incorrect because in steady flow, fluid properties at both the inlet and exit remain constant over time. B. Fluid properties at both the inlet and exit remain constant over time in steady flow. This is the correct answer because in steady flow, the properties at both the inlet and exit do not change with time. C. Exit properties change with time, while inlet properties remain constant. This is incorrect because in steady flow, both inlet and exit properties must remain constant over time. D. There is temporal variation in fluid characteristics at control volume boundaries. This is incorrect because by definition, steady flow implies no temporal variation in fluid properties. Water heater in steady state. In a steady state water heater, the mass flow rate entering equals the mass flow rate leaving. Electrical energy is used to increase the water temperature inside the tank. Some energy may be lost to the surroundings as heat loss. Even though energy flows, the internal condition of the system remains stable. This example shows a direct application of the energy balance to a real system. Work in compressible system. In flow systems, work can appear in the form of shaft work and electrical work. Shaft work is usually associated with rotating components such as turbines and fans. Electrical work is related to heating elements or motors. All these forms of work must be included in the energy balance. This shows that energy interactions are not limited to heat only. Energy unit equivalence. Energy units can be expressed in different forms that are physically equivalent. In the SI system, joules per kilogram is equivalent to meters squared per second squared. In the imperial system, BTUs per lbm can also be converted to mechanical units. This equivalence is important to maintain unit consistency in calculations. Unit mistakes can lead to very large errors in results.
High velocity effects. At high velocities, small changes in speed can cause large changes in kinetic energy. This is because kinetic energy is proportional to the square of velocity. In high-speed flows, this effect becomes very significant. Therefore, small changes in flow conditions should not be neglected. This concept is important in the analysis of nozzles and diffusers.
Check your understanding. Number 5. This question emphasizes the relationship between velocity and kinetic energy. The key point is that at high velocities, energy becomes more sensitive to speed changes. This is a direct consequence of the quadratic relationship between kinetic energy and velocity. This understanding is very important in high-speed flow systems. Without it, energy analysis can become inaccurate. Modern gas turbine. Modern gas turbines are designed to produce large power output with high efficiency. These systems use multiple stages of low-pressure and high-pressure compressors. High rotational speed allows effective conversion of thermal energy into mechanical energy. The compact design shows technological advancement in energy engineering. This example illustrates a direct application of control volume concepts in industry. Nozzle and diffuser dynamics. A nozzle is used to increase flow velocity by reducing the cross-sectional area. A diffuser works in the opposite way by decreasing velocity and increasing pressure. These velocity changes directly affect the kinetic energy of the fluid. In many systems, changes in kinetic energy cannot be neglected. These devices are often analyzed as steady-flow control volumes. Turbine blade features. The angle and shape of turbine blades are designed to extract the kinetic energy of the fluid efficiently. The fluid kinetic energy is converted into mechanical energy on the turbine shaft. Aerodynamic design ensures minimal energy loss. The blade material must withstand very high temperatures and pressures. This component shows the importance of interaction between fluid mechanics and thermodynamics. Throttling devices. Throttling devices are used to significantly reduce fluid pressure. Valves, porous plugs, and capillary tubes are common examples of such devices. This process usually produces no work and involves no significant heat transfer. The main effect of throttling is a pressure drop without mechanical energy change. These devices are very important in refrigeration and cooling systems. Throttling of ideal gas. For an ideal gas, the throttling process occurs at constant enthalpy. Since the enthalpy of an ideal gas depends only on temperature, the temperature does not change. This shows that not all pressure drops cause cooling. This relationship is very important for distinguishing the behavior of ideal and real gases. This concept is often the basis for analyzing expansion valves. Answer B. The enthalpy remains constant and the temperature does not change in throttling. Explanation. A. The temperature of an ideal gas changes while the enthalpy remains constant. This is incorrect because during throttling, the temperature of an ideal gas typically does not change and enthalpy remains constant. B. The enthalpy remains constant and the temperature does not change in throttling. This is the correct answer. In throttling, enthalpy remains constant and the temperature of an ideal gas does not change. C. Throttling leads to a change in enthalpy which affects the temperature. This is incorrect because throttling is defined as a process where enthalpy stays constant and it does not lead to a change in enthalpy. D. Temperature remains constant, but the enthalpy increases during throttling. This is incorrect because in throttling, the temperature typically does not remain constant and the enthalpy does not increase. Throttling process insights. In the throttling process, the total enthalpy of the fluid remains constant. There is no shaft work and no significant heat transfer. Internal energy and flow energy can transform into each other. A large pressure drop occurs without changing the enthalpy. This process is often used to produce low-pressure conditions in engineering systems. Shower T-elbow mixing. The T-elbow in a shower acts as a mixing chamber for hot and cold water. Two inlet streams combine into one outlet stream with a certain temperature. This mixing process can be analyzed using mass and energy balances. Usually, there is no work, and heat transfer to the surroundings is neglected. This example shows a simple application of a mixing control volume. Compressed liquid behavior. A compressed liquid exists at a temperature below the saturation temperature for a given pressure. In this condition, its properties are close to those of a saturated liquid. Pressure changes do not significantly affect its thermodynamic properties. Therefore, saturated liquid properties at the same temperature are often used as an approximation. This approach greatly simplifies engineering calculations. Simple heat exchanger often uses two concentric pipes. Hot and cold fluids flow to exchange thermal energy. The flow arrangement can be parallel or counterflow to control heat transfer effectiveness. This device is widely used in small-scale applications. Its analysis is performed using energy balances on each fluid. Heat exchanger analysis. Heat exchanger analysis strongly depends on the choice of control volume. If the entire heat exchanger is selected as the system, the net heat transfer to the surroundings can be assumed zero. If only one fluid is selected as the system, heat transfer will appear. Heat always flows from the hotter fluid to the colder fluid. Good insulation is required to minimize heat loss to the surroundings. Heat exchanger analysis. The selection of the control volume boundary determines the form of the energy equation. If the entire heat exchanger is taken as the system, there is no net heat transfer to the surroundings. If only one fluid is analyzed, then heat transfer between the fluids must be included. Heat always flows from the higher temperature fluid to the lower temperature one. Insulation plays an important role in maintaining system efficiency. Check your understanding. Number 7. This question emphasizes the consequence of system selection in heat exchanger analysis. If only one fluid is selected as the system, then heat transfer cannot be neglected. This shows that the result of the analysis strongly depends on how the system is defined. This concept often causes confusion at the beginning of learning. Understanding system boundaries is the key to thermodynamic analysis. Heat exchanger heat transfer. The amount of heat transfer depends on the selected control volume boundary. Heat can be added to or removed from the fluid depending on the analysis perspective. In practice, consistency in defining the system is what matters most. Mistakes in choosing the system boundary can lead to incorrect equations. Therefore, the first step in any analysis is always to define the system correctly. Heat loss in uninsulated pipes. Uninsulated pipes will lose heat to the surrounding environment. The larger the temperature difference between the fluid and the surroundings, the greater the heat loss. This loss reduces the overall system efficiency. In energy system design, thermal insulation becomes very important. This example shows how the environment can affect system performance. Work forms in pipe flow. In pipe flow, work does not always appear in only one form. Shaft work can be used to drive fans or pumps. Electrical work can come from heating elements or motors. All these forms of work must be included in the energy balance. This shows that flow systems have complex energy interactions. Temperature and enthalpy. For air within a certain temperature range, the change in enthalpy is proportional to the change in temperature. This approach uses a constant specific heat value. The error produced by this approximation is very small. Therefore, this method is often used in engineering calculations. This greatly simplifies energy analysis in air systems. Answer B. The change in enthalpy is proportional to temperature change, with low error margin for air in the temperature range minus 20 degrees Celsius to 70 degrees Celsius. Explanation. A. The change in enthalpy is independent of temperature change for air. This is incorrect because the change in enthalpy is directly proportional to temperature change for air, as stated in the question. B. The change in enthalpy is proportional to temperature change with low error margin for air in the temperature range minus 20 degrees Celsius to 70 degrees Celsius. This is the correct answer, as the change in enthalpy for air is indeed proportional to temperature change, and the approximation error is below 0.5% in the specified temperature range. C. A variable specific heat value is required for accurate enthalpy calculations of air. This is incorrect because the question states that a fixed specific heat value provides accurate enthalpy calculations, not a variable one. D. The approximation error for enthalpy change in air is above 5% for temperatures between negative 20 degrees Celsius and 70 degrees Celsius. This is incorrect because the approximation error is below 0.5%, much lower than 5% for this temperature range.
Tank charging process. Tank charging is an example of an unsteady flow process. The mass and energy inside the control volume change with time. Fluid enters through a supply line and changes the conditions inside the tank. The analysis of this process must account for mass and energy accumulation. This example is very important for understanding transient systems. Control volume dynamics. In unsteady processes, the control volume boundary may change shape or position. The system properties change continuously with time. This makes the analysis more complex than steady flow cases. This approach is more realistic for many industrial processes. This example shows that system definition can be dynamic. Closed system energy. If all inlets and outlets are closed, the system becomes a closed system. In this condition, no mass crosses the system boundary anymore. The energy equation becomes simpler because it only involves heat and work. Energy changes occur only within the system. This approach reconnects the control volume concept with closed system analysis. Uniform flow work contributions. In a uniform flow system, work can come from boundary movement, such as expansion or compression. In addition, work can also appear as shaft work and electrical work at the same time. All these work contributions must be included in the energy balance. This shows that a single system can have many energy interaction mechanisms. A complete analysis must always identify all forms of work involved. Steam temperature rise. When steam enters the tank, its flow energy is converted into internal energy. This process causes a significant increase in the steam temperature inside the tank. No shaft work is done, and heat transfer to the surroundings is usually neglected. This temperature rise is purely due to the transformation of energy form. This example shows how energy forms can change in an unsteady system. Check your understanding number 9. This question emphasizes the mechanism of energy form transformation when steam enters a tank. The focus is on the conversion of flow energy into internal energy. Without understanding this concept, the temperature rise would seem confusing. This is a very good example to reinforce the understanding of energy conservation. This process is also relevant in many industrial applications. References. The references show that the entire material is taken from a standard, internationally recognized thermodynamics textbook.
The main reference is the work of Chengel, Bowles, and Canelo, which is widely used worldwide. This ensures consistency in notation and analytical approach. Using a standard reference also makes it easier for students to continue learning independently. This book becomes the main reference for deeper study in engineering thermodynamics.